The objective of the experiment is to study an object moving at constant velocity, particularly an object falling in water. Objects falling in a fluid can move at constant speed if there's enough time to reach this terminal velocity. We are going to use a burette filled with water and use a support to make sure the camera is not going to move. The object is going to be a steel nail and a plastic connector. The forces involved are the weight that makes the diver fall, the buoyant force that pushes the object upwards, the friction with the fluid or drag force which acts against the movement. Although the diver fits well in the tube, depending on the trajectory, we can have some friction with the walls of the burette. So the nail is responsible for most of the weight, and the plastic for most of the buoyancy and drag. The buoyancy and the weight are constant in an opposite direction. If the object falls vertically, the friction with the wall is going to be null, and the drag force will increase with the speed, until it matches the difference between weight and buoyancy, keeping the velocity constant. In order to have a better visualization of the diver and make more accurate measurements afterwards, we make a close-up. The nail can be recovered with a magnet, and then the plastic connector goes up due to the buoyancy, and we can easily repeat the experiment. If we want, we can measure the upward movement as well. We've used tracker to make measurements. First of all, we have calibrated the distances. 10 marks in the burette are 10.6 centimeters. And we've put the coordinate systems, tilting it a bit in order to align with the burette. The image is tilted because the camera was tilted. We've selected the frames that we are interested to use, and after that we have marked some points using tracker and exported the data to a spreadsheet. We've changed the graph coordinates from X to Y to check the constancy of the vertical speed. In order to model the movement, we are going to use an iterative method. We are going to relate the position and velocity on a time with the position and velocity a little instant before, using the force involved. Now, all the forces add in the net force, and as stated in Newton's second law, this net force is proportional to the acceleration of the body. If it goes to constant velocity, the acceleration is going to be zero. For small enough time lapses, the variation on velocity equals the acceleration multiplied for the time lapse. If the time lapse is small enough, the change in position is proportional to the velocity. So we have the desired relationships between velocities and time, and position and time. In this last relationship, we have to put some velocity. The velocity at the beginning or at the end of the time lapse, or the average velocity in the time lapse. We are going to use the final velocity. We've made some changes in the program to include the initial conditions. The average velocity of the movement has been taken as the initial velocity. The net force has been set as 0. We've also made changes to plot the y coordinate instead of x. As you can see, the comparison between the real data from tracker, red dots, and the data from the simulation are excellent. There are some minor deviations that can be due to the precision when positioning the points with tracker, or due to the tiny lateral movement of the diver. If we flip the axis, we will have an overall change of sign. So in the new coordinate system, the movement is going to greater y values and the speed is going to be positive. That's equivalent to flip the camera. If the net force is not null, the velocity is not going to be constant. The time position graph is not going to be a straight line. If we use other fluids like olive or sunflower oil, the thermal velocity in each fluid is going to be different, depending on the viscosity of the fluid and the